Let's do a typical example then. Let's determine the deflection of a smoke curtain knowing the following criteria. Well, the density of ambient air, we'll just assume for this, is 1.2 kilograms per metre cubed. Theta, the temperature rise, is 240 degrees. The depth of the gas layer is 2.5 metres. The local smoke temperature is 520 degrees Kelvin. The weight per metre length of the curtain's bottom bar is 2.2 kilograms per metre. And the weight per metre squared of the curtain fabric is 0.6 kilograms per metre squared. Now let's assume that the curtain is 0.1 metres larger than the height of the smoke layer, which is 2.6 metres. Now if you put those variables in this formula, as you can see here, that will give you a deflection of 0.697 metres. That is the deflection. So it's going to deflect by 0.697 metres. Now that's the formula to determine the deflection of the curtain. Now you need to determine the length of the curtain to contain the gas layer. So you don't just have this on, you have to work out now how long the curtain's got to be based on this deflection. And this can be determined by the following. This is the formula here. Now what you first of all, you've got LC, which is the length of the curtain required to contain the gas layer, equals, you've got D, which is the depth of the gas layer, plus DC, which is the deflection of the curtain, which we worked out earlier, and that's multiplied by tan, and then you see the brackets there, the antitan of DC divided by D divided by 2. That's the formula you need to work out. Now, when you use this formula, it's an iterative process. In other words, you have to make assumptions of values to put in a formula to get a value. So it's like there's two unknowns. So you have to use an iterative process and just keep doing the calculations until they nearly equal each other. That's how it works, an iterative process. And this is how you apply it. First of all, you have to assume a starting value for LC, the length of the curtain. Now, like I say, normally you'd start with at least the smoke layer depth plus, say, 0.1 metres. It saves you some time. So add something on. So 0.1 metres above the smoke layer depth. Then secondly, you calculate the DC using this formula here, using the formula again, with that value of LC in that formula. So you work out the deflection of the curtain. Thirdly, you calculate the next value of LC using this equation again. So do you understand? You use the DC, the LC, and you keep doing it. You keep doing those calculations, LC, DC, LC, DC, LC, DC. Repeat these steps until the new value of LC differs by an acceptably small amount. In other words, when it gets to only 1% difference, you can accept that calculation. That's how you do it. It's an iterative process. So you use that calculation, you assume a value for LC, you put it in that DC formula, then you put that value in the LC, and you keep going, and when it doesn't change by more than 1%, in other words, you got so close, you can accept it. Now, once you've determined the new value of LC using that iterative process, this has to now be modified by including a term to allow for bowing of the curtain. And this is as follows. This is the final length of the curtain, which is LC final. And that is equal to LC, which is the calculated length of the curtain. So that's not your assumed value, that's your calculated length, plus 1.7 times, in brackets, LC minus D, which is your smoke layer depth. That takes into account the bowing. And that gives you your final length of your curtain. And it's critical that you do this, because if not, it's not going to be long enough. It hasn't taken into account the bowing and the deflection. Basically, you're going to get leakage. So that's what you have to do. Now, to carry out this exercise takes a lot of calculations, and you would be advised to possibly use a programmable calculator, or there is an online smoke calculator which does this for you, this iterative process, so you can use that. Now, that covers the situation where the curtain is used to create a smoke reservoir. In other words, it doesn't drop all the way down, all the bowing, that takes into account there, does not reach down to the ground. That's what that calculation does there. Now, the second situation, which is what I'm going to cover now, is where the curtain is used to completely close an opening. Now, in this situation, the smoke layer extends below the bottom of the curtain. To determine the deflection, now you've got to use this formula. This is the formula. And it's a similar formula to our previous model with the same variables, but there's added calculations in there. That's the formula there to work out the deflection of the curtain when it completely goes down to the bottom. So let's look at the variables then. DC is the deflection of the curtain. Then first of all, you've got the density of ambient air. That's multiplied by theta, which is the temperature rise above ambient of the gases in the smoke layer. Your D is your smoke layer depth. Now your H is your height of the opening. So that's the actual height of the opening that you insert in there. T is the temperature of the smoke layer in Kelvin. And B is the weight per unit length of the curtain's bottom bar. And again, we've got weight per unit area of the curtain fabric, which is MC, and LC, which is the length of the smoke curtain assumed, measured along the fabric. So this is the new formula. Now, to determine the length of the curtain reaching the floor that's required, you use the same process as before, that iterative process. Again, you assume a starting value for LC. You calculate DC using that variable in the equation. Then you calculate LC using the equation with the new DC. And you keep going step 1, step 3, step 1, step 2. You keep going until you get an acceptable variation, which is when it doesn't change by more than 1%, you can accept it. And again, once you've determined this new value of LC, which you needed, this has to be modified by including a term to allow for bowing of the curtain, again as follows. Now in this case, you don't use D, but you use H. So you don't use the depth, you use the height of the opening, which is the height of the opening in metres. So this is the LC final here. LC final equals LC plus 1.7 times, in brackets, the LC minus the H, which is the height of the opening. That takes into account. Now that covers the impact of the deflection of the smoke curtain, which I'm sure you'll agree is an important aspect and has to be taken into account. You can't just say, get a smoke curtain, 6 meters, that'll do. It has to be taken into account the bowing, the deflection, the buoyant gases. Otherwise, it's not going to achieve the design criteria and you will get smoke spreading around the building. This is sometimes ignored and it can prove fatal, as have some of the criteria can be life safety and it can't be established if you haven't got the correct length of curtain. If it's not considered, clearly it can lead to smoke spreading to areas where the design strategy clearly does not want it to.